Hello everybody, let's go ahead and take a look at today's notes. It's St. Patrick's Day, what do you know? So we're talking about translations or transformations of functions. So we talked about the fact that some functions, all we can do is see a picture of them, not the equations, and what do we do with them, okay? To translate just simply means to move it. You don't change the shape, you move it. But transformations means actually to change the shape. So we're going to do a little bit of both. We're going to do a transformation and a translation. So if it's a negative f of x, that means the y values are negative, so it's a reflection over the x-axis. Okay. If it's an f of a negative x, that means the x's are negative, so it's a reflection of the y-axis. If it's the absolute value of x, then it means all of your y values that are negative become positive. So, anything that comes in has to come out positive. You have to have positive y values, okay? So we graphed them. First one we did was we took our function, f of x, and we had to do a negative f of x. We literally flipped it over the x-axis. So we redrew our figure, and here it is, rotated over the x-axis, okay? Our second graph we took was f of negative x. So we took our function, and we rotated it around the y-axis, and we redrew our function, and it looks like this. The third graph we took was the absolute value, so any negative value on our graph just became positive. Any negative value on our graph became positive, so our graph looks like this. These negative values folded up, these negative values folded up. Okay. On the back side, it's a little sloppy, I'll do my best. We talk about even functions, okay? So one definition of an even function is that it's symmetrical with the line over the y-axis. So the equation that I graphed here was looks something like this, and I didn't draw it real well, but if you were to rotate this around the y-axis, it spins onto itself, so it is an even function. So it has symmetry over the y-axis. Even functions are. There's a proof to that, and that is if f of x is equal to f of negative x. What does that mean? Here's our proof. If we can make f of x be equal to f of negative x, we've proven that it's even. So this proof means make all of the x's negative. So I took an equation that was even. That's actually the equation of this. And I made all of my x's negative. And then, of course, we know a negative times a negative is a positive, and negative times a negative is positive. So we were able to show that f of x is indeed equal to f of negative x. So we've proven that this function is even. Okay? Now, on the next one, if it's an odd function, okay, so I drew a picture of an odd function. Here's an odd function. We said if you can rotate it 180 degrees around the origin, then it becomes odd. And sure, if I spin this 180 degrees, it spins onto itself. So I found the equation, x cubed minus 8x, which is the equation of this graph right here. To prove it is an odd function, negative f of negative x has to equal f of x. So I did this in two steps. First, I did the negative x. Okay, so I put the negative, made every x negative, and a negative times a negative times a negative is a negative, and that makes a negative negatives a positive 8x. And then the second thing, because I have to do two things, I then did the negative f of x. So I made the whole thing negative, I multiplied it by negative 1, and then it turned out to have a positive x cubed minus 8x. So sure enough, the original function f of x is equal to a negative f of negative x. Okay. The last thing we talked about is over the x, y equals x. So that's this line right here. We learned last year that any function reflected over that line is its inverse. So we talked about the fact that we have this thing called an inverse, and to do an inverse, we just switched x and y. So the x, y values switch. X becomes y, y becomes x. So I graphed my first equation, started at -4, and I went up 2 over 1, up 2 over 1. Okay, here's my original function in blue. And then I took a look at some specific points along this line, and I switched them. So I switched them. I switched x with y, I switched x with y, I switched x with y, and I switched x with y. And then I regraphed these. Okay, so then I graphed the point -4, 0, -2, 1, and so forth. And I wound up graphing this purple line. This is the inverse of my original function. And they are indeed reflections over the line y equals x. Now, instead of doing it point by point by point, we could just go and switch them right off the bat. So take the equation and switch x and y. So I switched x and y. I made yx and xy. And then I really need to solve for y, so I can graph it. So I add 4 divided by 2, and then I graph that. Concurs exactly to that equation here. So I wrote as f inverse of x is 1/2 x plus 2. That's the inverse of 2x plus 4. Finally, on example 3, these two equations, y equals x minus 2 squared plus 3, turns out to be this graph. Its inverse, now notice I switched the variables, its inverse would be an x equals a y minus 2 squared plus 3. So to graph that, I found my individual points on my original function, and I switched my points, and I was able to graph its inverse equation. Okay, so that's all I have. If you have any questions, there's the homework, and come see me. Okay.